Alright, what's going on, everybody? In this video, I'm going to be giving you an introduction to limits. Let's get a closer look at the topics that we're going to be doing in this video. Okay, so the first thing that I want to talk about is, what limits actually are, right? It'd be a good idea if we know what those things are. We'll discuss the notation that comes along with it, and then we will do some quick practice, right? We'll have like the graph of a function, and then we'll have to find different limits using that graph, right? That's an extremely popular question early on when talking about limits. We'll also look at some end behavior questions and some other stuff there. Okay, we'll look at different cases where we have a denominator of zero, right? If we have a denominator of zero, that's important for different things like vertical asymptotes, which we'll talk about eventually, but that is going to be important to look at. Okay, and then we will kind of shift a little bit and talk about one-sided limits. Okay, one-sided limits are important for different things like continuity and vertical asymptotes. We'll do some practice with that, and then lastly, we'll do things where we have the denominator of zero, except we'll be doing them with one-sided limits instead of like a full limit. Okay, so that's what's coming in this video, and if you want to view the blank PDF where I just have all the questions listed so you can go try them before we actually do them, that PDF is in the description down below. So the first thing that I want to talk about in this video is what limits actually are. Okay, so limits are an extremely useful tool that allow us to write down not what the value of a function is at a certain point, but what value a function becomes as it approaches a certain point, right? And so let's say that we have the graph y equals x squared, right? I have it graphed here. Okay, usually with a function, we'll say, okay, well, what happens when we have an x of 2, right? What's our y value? Okay, with limits, we say something different. So let's talk about infinity, right? We'll say that, as x approaches infinity, right, as we go this way, what happens to y? What does y approach, right? What does y become? What happens in this direction? Okay, and as you can see, as we go this way in the x direction, y is going to infinity. Okay, and so what we would write here is that y approaches infinity. All right, and so that's kind of what limits are. Right? You could also say something like, well, what about as x approaches 2, right? As we go to here, right? Well, as x approaches 2, right? As we get closer here, this way and this way in the x direction, right? And when I say that, I mean kind of along the curve here, right? Well, what happens to y? Well, y is going to get closer and closer to the value at x equals 2, which is, well, let's plug in 2 here. That's going to be 4. All right, and so that's the idea of what limits are, right? We're not saying, what that value is going to be, but we're saying what it approaches, right? And I'll make that a little more clear in just a second here. Okay, so, while limits are great for discussing end behavior, right, like we just did there with, as x approaches infinity, blah, 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 that's far from their only purpose. We don't just use limits for end behavior. We use it for a lot of different stuff, right? And so, like I just did with that example with the parabola, okay, we can do the same thing for y equals x cubed, right? As x approaches 1, let's say that 1 is right here, okay, what does y approach, right? What does y become? So as we move along the curve in these directions, right? So that would mean like this way and this way, right? What does the value of y get closer and closer to? Well, it would be the value of that graph at x equals 1, which is, well, 1 cubed, that's 1. Okay? Cool. So we'll move on to the next example here over here. Okay, with this graph, right, we have an open circle here, which means there is actually no point here. So as x approaches 2, what does y approach, right? As we get closer and closer to 2 from both directions, what happens to y? Well, based on our definition, right, we're trying to see what is y getting closer and closer to. And even though there's no point here, we're still getting closer and closer to 4. Okay? We're not saying, well, what's the actual value here, right? We're saying, what is this thing getting closer to, right? And that's y equals 4. Even if we had a point that was like up here, right? And you'll see that a lot with these graphs. We'll have like an open circle down here and then a closed circle up here, right? This graph is not getting closer to this point as x approaches 2, right? It's getting closer to this point, right? Even though there's nothing there, it's still what it's getting closer to. Moving on, this is actually something that's going to be really important with derivatives, right? This is slope, right? Delta y over delta x. And so, a question we might want to ask is, as the change in x approaches 0, what happens to the change in y? Right? That's not something that you need to actually care about just yet, but I just figured I'd give you a little insight there. So moving on to limit notation, right? We have an idea of what limits are. Now let's talk about what the notation for limits actually is. Okay? And so really the theme here has been something like, well, as x approaches a, y approaches l, where I'm saying, x is approaching some value, we'll call that a, and y, as x approaches a, y is getting closer and closer to l. Right? It's the same thing. I'm just putting letters in, right? Instead of having 2 and 4, I have A and L. Okay, so don't get too confused with that. Okay? We just use letters when we want to write something in general, right? We want to be able to plug different numbers in here. Okay? So how we write this, okay? We say, well, as x approaches A, right? The limit, okay? This limit, where is, y going? Okay, well, it's going to L. So how we actually say that, because that was kind of gibberish, right? We say the limit as x approaches A of f of x equals L, right? And so think of that f of x as our y. So we just kind of write our function here, right? And on the right here, that is where y is approaching. Okay, so we have where x is approaching down here. We define what our y is right here. So maybe that would be like x plus 2 or x squared plus 2x over x plus 1 or, whatever, right? And we have what y approaches on this side. Okay, and I got to erase all that now. All right, cool. So now that we have the notation done now, let's move on to some quick limit practice, okay? The first example that I have for you here is just an end behavior question, right? We're looking for the limit as x approaches infinity of this polynomial, right? So this means as we go to infinity in the x direction, right? As we go this way, what happens to y? Does it go, up, down? Does it go to infinity, negative infinity? Does it kind of level off somewhere? Or what does it do? Right? Well, remember what we know about end behavior from, I believe this is algebra 2, or, some algebra class that you may have taken in the past. Okay? Well, for end behavior, we look at that first term here. Okay? And that should make sense because as x gets bigger and bigger and bigger, these contributions, right, from x squared, x, and 1, that doesn't matter, right? Think of how different x squared and x are when you just plug in like 10 or something like that, right? 10 squared is 100, but if you just plug in 10 for x, you just get 10, right? So these things are drastically different. Imagine now x cubed. Well, that's 1,000, right? 1,000 is so much bigger than these things. So, as x gets bigger and bigger and bigger, this difference between this stuff and this stuff gets even more drastic. And so really, all that ends up mattering is what your first term is. Okay? And, here, when we have the graph of an x cubed, right, we know that it starts looking like this, right? But since it's negative x cubed, we know that it looks like this. And so, as x approaches infinity, right, as we move along this graph in the positive x direction, we are going down. We're going down to negative infinity, right? So our answer is going to be negative infinity here. Okay? So hopefully that makes sense. It's a little bit of a review of end behavior, right? There's a lot that comes with end behavior. Hopefully it wasn't too much of a burden for you when you were taking algebra. Now moving on to example 2, let's find the limit as x approaches 1 of negative x cubed plus 2x squared minus x plus 1. Okay, so same polynomial, same thing that we're trying to find, what this approaches, but now we have x approaching 1 instead of x approaches infinity. Okay, well, let's see. This graph, again, it's going to look something like what we drew above, right? It's going to look something like this, right? Something like it. Okay, it's going to have the same end behavior. And so, if we want to see what this y value is going to become as x approaches 1, so like as we approach here from either side, from this way and this way, well, we can just plug in 1 everywhere we see an x. Why? Because this graph of a polynomial is completely continuous, right? There's no open circles, there's no discontinuities, there's nothing we have to worry about here, right? We know that, there's no, and there's no jumps in this graph either, right? And so we know that this limit, right, is going to be, this, let me see if I can word this in the best way possible, right? As x gets closer and closer to this value, right, at x equals 1, as x gets closer and closer to 1, our y value will get closer and closer to the point at x equals 1. Okay, and you'll see why that's not always going to be the case later. Like if we have a function where we have like a jump discontinuity where it jumps like this or whatever. Anyways, if we just plug in 1 here, we can say that, actually I'll write it like this. We can say that this is equal to negative 1 cubed plus 2 times 1 squared minus 1 plus 1. These things will go away, and then you have a negative 1 plus 2, right? That's there, that's there. And so that equals 1. Okay? So these are our answers for 1 and 2. I apologize a little bit for the stuttering here. For some reason, I'm a little antsy tonight. All right. So now we're going to do one of those graphing limit problems. Okay, these are extremely common. I definitely would see you having something like this on a homework or whatever. Okay. Well, given the graph of f of x, we want to find the following limits. Okay? Well, let's look at this one first. The limit as x approaches infinity of f of x. Right? Again, this limit is saying that as x goes to infinity, what happens to y? What happens to f of x, right? Those are the same thing. Okay? Well, what's happening to y? As we're traveling along x in the positive direction, we're going off into infinity, right? We're traveling this way. What's happening to y? It's going to infinity. So, that's infinity. Okay? What about as x approaches 0? What's happening to y? Well, there's a point here, right? And so as we move along the graph in both directions, right? We move along closer to x equals 0, right? We are approaching y equals 3, right? If you ever each one of these tick marks is 1. Okay? That's what y value we are approaching. Now what about as x approaches 3? Well, in that case, we are, that's this open circle right here, right? We are getting closer and closer to what? Well, as we move along the curve in both directions, we are approaching y equals 1, right? It doesn't matter that there's an open circle there, right? We care about what this curve is approaching as it approaches x equals 3, not what it actually is at x equals 3. That's something different, right? If we asked what it actually is, it'd be this point up here. Okay, so this answer is 1, right? That's y equals 1 right here. Awesome. Now what about as x approaches -2, right? Well, -2 is right here, right? And in this case, we're going from this direction in this direction, okay? And are they approaching the same thing? No, they're not, right? From this side, we are approaching an open circle that's at y equals 2. And from this side, we are approaching a closed circle at y equals 3, right? And so the two sides don't agree with each other. And so what this means is that the limit does not exist. If we write a DNE for that. Okay? So hopefully that makes sense. I'm not trying to make this confusing, obviously. Yeah, I mean, really, that's what we're trying to do here. We're trying to see, as x approaches a certain value, what does y become? Okay? What does this thing become? All right? So, assuming that you're okay with that, let's move on to cases where we have a denominator of 0. Okay? These are really important with limits, and so we want to check them out. So what if we have something where the denominator is 0 and we're not given a graph, right? So we can't easily see what the limit is as x approaches, in this case, 3. Well, let's take a look, right? What we can do with this limit, right? We can see that if we try to plug in 3 like we did with polynomials, right? Like we did in this example where we could just plug in 1. Here, we'll either have, there's a couple things that we could have. We have some kind of discontinuity, because if we plug in 3 here, we get 2x over 3, instead of x, you plug in 3, right? And so you get a 6 over 0, and that's bad, right? So that's not true. This is not going to be equal to that, right? It's not undefined, okay? So we have a problem. Right? And so since we get something that's undefined, what ends up happening at x equals 3, we just draw this here, right? What ends up happening here is that this graph is going to come in, and it could do a couple of things, right? It could come in and it could have an open circle there and then go, and that's called a removable discontinuity. It could come in here and then just boop, and then whoop, and that's called an infinite no, I drew that wrong. And it could go whoop, there we go. So that is called an infinite discontinuity, where one goes to negative infinity, the other goes to infinity. There could be other cases where they both go to infinity. That's kind of rare, but that can happen too, right? But them going off into infinity is a infinite discontinuity. Right? There is another kind of discontinuity. That's generally with piecewise functions. That's something like this, where we'll go to this line, where you'll have something like this, right? But that's not going to happen with this case, right? If we get a denominator that is 0, we could end up with a vertical asymptote, which, by the way, is a infinite discontinuity. It's this thing, right? Or we could end up with that removable discontinuity that I just showed, right, where it's just a circle. So anywho, we want to find out, what is this here? Is it a removable discontinuity? Is it infinite discontinuity? So what we're going to do is use some test points, right? Let's just try it out. Okay, let's get closer and closer to 3 from the left side and see what happens. Right? So this is, we'll try different things. Like, first off, we can try x equals 2. Right? We can try x equals 2.5. We can try x equals 2.75. And then x equals 2.99. And then x equals 2.999. Right? And then we'll try to see what happens to y. Well, if x equals 2, right? we could just plug in a 2 here and here, right? And we would get 4 over a negative 1. That's negative 4. Okay, so we have negative 4. That's a cool starting point, right? But then, if we plug in 2.5, right, we'll get a 5 in the numerator, and then in the denominator, we'll get a 0.5, negative 0.5, right? And so that would give us about negative 10. Okay, so this is starting to get a little bit bigger. If we plug in 2.75, we'd get y equals 2 times 2.75. I'm not sure what that is off the top of my head, but actually I think it's 5.5. And then this is going to be negative 0.25, right? And so if you start, if you like put this in your calculator or something, you'll see that, this denominator is getting much smaller, right? If we plug in 2.99, we'll get something in the numerator here, but then we'll get negative 0.01 in the denominator. And if we have 2.999, we'll get something divided by negative 0.001, right? And so what's happening here is that this whole thing, right, because these denominators are getting smaller and smaller and smaller, what's going to happen is, when the denominator gets smaller and smaller and smaller, the value of the entire fraction just blows up, right? Like, think about if you have 1 over, let's say 1 over 1,000, right? When you have a large denominator, right? This is something that's extremely small. But if you have 1 times 0.001, right? That's something that's, comparable to something like 1,000 divided by 1, right? That's the same exact idea. So this thing is, I believe, equal to 1,000 or 100 or something like that, right? So the whole idea is that when you have a really small denominator, you end up with something that's really big. Okay? So anyways, that's that. So what we're seeing here is that this denominator is blowing up. It's also negative, right? And so what we end up getting is that as x approaches, we'll actually say this here. We'll just write it out because we'll talk about what we're doing right now is actually one-sided limits. We'll talk about that more in the next section. But we'll say as x approaches 3 from the left, y approaches negative infinity. Okay, cool. Now let's try the right side. We'll try the right side on for size. And yes, I've realized I'm writing in gray and not white. I don't know why that is. So let me just switch that all over to white. So if you're having a heart attack right now, you stop. So if we switch over to the right side, the same exact thing is going to happen, right? Let's try some new test points. We'll try x equals, instead of 2, we'll go 4. And we'll do x equals 3.5, x equals 3.1, x equals 3.01, right? And as you can see, let's just focus on the denominator here, right? We get denominator of 1 here. Our denominator is, remember, we have an x minus 3 here. That's our denominator. We'll get a denominator of 0.5 here. This will be a denominator of a 0.1, right? This will be a denominator of 0.01, and if we keep going here, this will be a denominator of 0.001. Okay? And so as x is getting closer and closer to 3 from the right side, from the positive side, this thing is going to blow up again. Right? We're just going to keep going. This denominator is going to keep getting smaller and smaller. And so since this denominator is getting smaller, this entire fraction is getting bigger and bigger and bigger. And so what ends up happening is we're going to see that as x approaches 3 from the right, this function is going to approach infinity. Right? Because we're dealing with positives here, whereas in the last problem here, we were dealing with negatives. So we'll write the same thing here. I'll just copy this over. Okay, so as x approaches 3 from the right, y is going to approach infinity, not negative infinity. Right? And since these things do not agree, right, since this left side does not agree with this right side, right, they do different things, well, then we say the limit does not exist. Okay? So we'll say, I'll write it over here. Since the limit of both sides is not equal, that means that the limit as x approaches 3 of 2x over x minus 3 does not exist. Okay? So it doesn't exist. And, that's too bad, but really that does give us some information, right? This graph, we know now that, here's x equals 3, right? I don't know exactly what this graph looks like, right, with the 2x part, but at least we know now that as we go to 3, right, as we approach it from the left side, this thing is going to go down to negative infinity. And as we approach it from the right side, it's going to go up to positive infinity. And so there's going to be an infinite discontinuity at this point right here. This is called a vertical asymptote. Okay? So now we'll get into the whole one-sided limit thing, and this is going to be, what we were just doing here with the test points, right? Basically, in this last problem, we were essentially taking one-sided limits. In other words, we were looking at what y value we approach from a specific direction. We were looking at what we would approach from the left and what we were approaching from the right. Okay? And so how we would write this, okay, with our limit notation, right? We said that as x approaches 3 from the left, y was approaching negative infinity, right? And so we write that as the limit as x approaches 3 from the left side, from the negative side. So we put a minus there. And we say 2x over x minus 3. That's our function, right? And then we have negative infinity there. Okay? So that's a one-sided limit from the left, and then we can do a one-sided limit from the right. And so we said that from the right, so we'll do from the positive side, right, the right side, we get that this thing is equal to infinity, right? And so since these limits, right, from the right side of 3, right, from the positive side of 3, from the negative side of 3, they don't, right, and when we say negative here, right, like we're including when x equals 2, when x equals 2.5, right, because that's the left side of 3, even though there's a negative side there. So don't think that we're talking about x equals 0 here. That's not what's going on here. Like, it's not that, oh, we're approaching it from the left, so we have to be over here. No, we can be approaching it from the left and be talking about x equals 3, right? So hopefully that doesn't confuse anybody, right? Well, we're just talking about from the left direction when we put a negative side there, because the negative direction is on the left. So since these limits don't match up, right? Since the limit as x approaches 3 from the negative side of 2x over x minus 3 does not equal the limit as x approaches 3 from the positive side of 2x over x minus 3, the limit as x approaches 3 of 2x over x minus 3, right? This is the full limit that considers where it approaches from both sides, right? This limit does not exist, right? There's no one value that we can say that this graph is approaching as x goes to 3 from both sides, because, as we saw here, these graphs are going to go in different directions, right? As x approaches 3 from the left side, it goes down to negative infinity. As it approaches from the right side, it goes up to positive infinity, right? So since they're not going to the same place, there's no limit. There's no overall limit, rather. Okay? And so more generally, when we say how I'm saying this, is that this full limit, right, as x approaches some value a, it'll exist, right? It'll equal some value L if and only if that these two limits from the right side and the left side agree on that L, right? They have to agree on that y value. Okay? So that's what has to happen for us to actually get a full limit. Now, moving on to some practice with one-sided limits, let's do the same graphic exercise, but now we're going to do it with one-sided limits. So, given the graph below, we're going to find the following limits. We have quite a few here. Right? We're going to look first at x approaching -1 from the positive direction. Right? What does f of x equal? Okay. Well, if we're approaching -1, which is this x right here, we're approaching it from the negative direction, or from the positive direction, from the right side. We're just going to travel along the curve, right, going in that x. We're coming from the right, and we end up at y equals -1. Right? We end up at this open circle here. That's what we're getting closer and closer to. And so this thing is going to equal -1, right? That's what y value we are approaching. As x approaches -1 from the negative side, well, we're coming from the left side this time, right? And so now, if we follow the curve from the left side, right, we're getting closer and closer to a different point. We're getting closer to y equals 3. So that's 3. But what about as x approaches 1? Well, remember, for this, this was supposed to be -1, I think. Yeah, that was supposed to be -1. Sorry, but yeah. So as x approaches -1, what happens, right? Well, these things don't agree, right? The left side doesn't agree with the right side, and so that means that the limit does not exist. Okay? Now, what about x approaching 2 from the negative side, right? Well, as 2 approaches, right, this is x equals 2. As it approaches 2 from the negative side, what happens, right? Well, we're getting closer and closer to a y value of, looks like 1, right? So that's 1. Again, it does not matter. Let me just get rid of that. It doesn't matter that we have a point down here. The point does not matter. We're not asking what the value of the function is at x equals 2. We're asking what does it approach as we move along the curve towards that x equals 2 mark. Okay? And if we move from the positive direction to get to 2, well, we are approaching the same point, right? We're approaching y equals 1. And so since these two limits agree, when we talk about the limit as x approaches 2 entirely, right, that's also going to be 1, right? From both sides, we are approaching y equals 1. Again, it does not matter where the point is actually defined. It matters what this curve is approaching. All right, let's also talk about the limit as x approaches 0 of f of x, right? Just kind of like a regular limit. Well, right here, there's no open circles or anything, right? We're just looking at what happens as we get closer to x equals 0 along the curve. And again, we agree on a point here, right? We agree on y equals 1. Right? From both sides, we get closer and closer to y equals 1 as we move along the x-axis to get to 0. Okay? So that is the idea with one-sided limits. Really, whenever we see a plus, we're moving from the positive direction, right? This is the positive side, so we're moving left. Okay? And if we see a negative, we're moving from the negative direction, right? The negative direction is over on the left, so we need to move right. Okay? Anywho, moving on to our last section here. One-sided limits with a denominator of 0. Okay, so now we're going to talk about, we're going to combine the denominator of 0 stuff from before, But now we'll do it with some one-sided limit stuff, okay? And this should be a little bit easier because before we had to do all these test points and write our limits out with words. Now we have actual notation for it, okay? So I'll make this quick and short and sweet here. We have limit as x approaches 0 from the positive side of 1 over x, all right? And for this, right, if we're getting closer and closer to 0 from the positive direction, we have test points like 1 over 1, 1 over 0.5, 1 over 0.25, right? And we're getting closer and closer to x equals 0, okay? And as we get closer, this denominator is shrinking, right? It's positive though. And so what that means is that, well, this whole fraction starts to blow up, right? It starts to get bigger, right? 1, that's 1, that's 2, that's 4, this is 10, okay? And so it just keeps going from there. And so it starts blowing up. This becomes infinity. Okay? But what about from the negative side? Well, now we're approaching it, but we're approaching it with negatives. So, we'll have different numbers like -1, -0.5, -0.25, -0.1, right? We are getting closer to x equals 0 from the negative direction, right? From the left of x equals 0, which is the reason why I'm saying x equals 0 is because that's what the limit says, right? Before we were talking about like x equals 2 and x equals -1, right? So it all depends on what that limit says, right? But now that, this thing is still blowing up, right? Except now we have negatives, we have one negative, and so what that means is we're going to approach negative infinity instead. Okay, and since this right-hand side does not agree with the left-hand side, the limit as a whole does not exist. All right, cool. So that's that, but we'll move on now to 1 over x squared instead of 1 over x, right? And here, you might already see this, you might not a big deal. We have x squared, so we don't end up with anything being negative, right? We talk about the limit as x approaches 0 from the positive side, right? Now we'll have things like, 1 over 1 squared, 1 over 0.5 squared, right? We have the x value still approaching 0, right? But now from the positive side, so we get positive values of x, right? That are just getting smaller and smaller. Right? So here you can see, that denominator is just getting smaller and smaller. And so this thing blows up again. And so we get infinity. But if we approach it from the negative side, now we're looking at negative numbers. But when we have negative numbers, in this case, when we have x squared, well, that just is going to make everything positive again, right? Right? All of these values are going to be positive because it's a negative that's being squared. And so the limit as x approaches 0 from the negative side of 1 over x squared is also going to be infinity, right? These are all positive numbers. These are all blowing up. And so these are going to infinity, right? And since these agree, right, these two limits are infinity, that means that the entire limit we say is also approaching infinity, right? From both sides of x equals 0, the graph is starting to approach infinity. And so what you'll actually see with these graphs, right, 1 over x is going to look like this, right? It's going to look like this, right? Where from the negative side, we go to negative infinity. And from the positive side, we go to infinity. Now, in contrast, 1 over x squared, it's still going to go to infinity from the right side, but it's also going to go to infinity from the left side. Right? And so that looks pretty gross, but yeah, let me see if I can do something a little bit better. right? There you go. That is what 1 over x squared is going to look like. And so you get that thing that I mentioned before that's kind of rare, I guess. But you get that, you get an infinite discontinuity still, right? This is an infinite discontinuity. And right here, you're still getting two things that are approaching infinity. All right? You still get a discontinuity here, right? At x equals 0. Okay? But now you have the two things going to the same direction, right? They're both going to infinity, and so the overall limit as x approaches 0 is going to be infinity as well. Okay? So that's really the overview of limits, as a recap, as a quick recap. What we talked about what limits actually are, right? We talked about how we're looking for what things are approaching, right? What y values we are approaching as we approach a certain x value. We did some practice with limits. We talked about how, again, it does not matter if the point is actually defined. It matters, what that graph is approaching. We did the notation. We did some quick limit practice, right? We talked about M behavior. We did an example there, okay? And then we just saw that, well, for graphs that are, completely continuous, right? They don't have any discontinuities that we need to worry about, right? They're not undefined when we plug in x equals 1, right? We can just end up plugging x equals 1 in, or x equals whatever in, right? Like a polynomial is a great example of that. We did some examples with graphs, right? We looked at overall limits. We saw that if the limit does not approach the same thing from both sides, then it doesn't exist. We talked about what happens when we have a denominator of 0 and we have to use test points. Now, that's not always going to be true. We don't always need to use test points. But we'll talk about, evaluating limits algebraically in another video, in the next video. Okay, and then we moved on to one-sided limits, which were a nicer way of writing our test points, right? So we didn't have to write it like this. We could write it instead like this. Okay, and after that, we talked about how these two limits from the left and the right-hand side have to agree on a certain value for us to actually say that the overall limit exists, and it would also be at that certain value. Okay. We did some practice with one-sided limits, right? We said that if it's from the positive direction, that's from the right side. If it is the negative direction, it's from the left side, right? And then we just did some practice here, right? We used test points again, but this time we used our one-sided limit notation. Okay? So that is about it for this video. Now remember, I do have that full Calculus 1 course, or if you're in pre-calc, I have a full pre-calculus course in the description down below that you can go check out, and hopefully this video has helped you. I really appreciate all the support, guys. Thanks so much for watching. I'll see you soon.